In this video, we're going to discuss the third law of thermodynamics. The third law of thermodynamics tells us that the entropy of a perfectly ordered crystalline substance at 0 Kelvin, at absolute zero, is zero. And we should appreciate this because we understand the relationship between temperature and entropy. At higher temperatures, the molecular motion is much greater, and so these substances have higher entropy. As we lower the temperature, molecular motion slows, there's less randomness, and lower entropy. And this process will continue until we get to absolute zero. At absolute zero, the substances are perfectly ordered crystals, and so there's no molecular motion, and the entropy is equal to zero. Now we can also see this using the Boltzmann equation, which we've introduced previously, where S is our entropy, K is a Boltzmann constant, and then we have the natural log of W, where the W is the number of possible arrangements or microstates for a system. Well, if we look at the Boltzmann equation for a substance that is at 0 Kelvin, well, at 0 Kelvin, substances, there are no molecular motion, and the substances are arranged in perfectly ordered crystalline substances or crystalline configurations. So when they're perfectly ordered crystals, there's only one possible microstate. So W is equal to zero, or excuse me, W is equal to 1. So if we take the natural log of 1, we get 0, and therefore the entropy, mathematically, we calculate to be 0 at 0 Kelvin when we have a perfectly ordered crystal. And we can see this if we plug in our numbers. The Boltzmann constant you see here, we take the natural log of 1. Again, for a perfectly ordered crystal, there's only one possible microstate, and that will give us a value for our entropy of 0, and the units there would be joules per Kelvin. So we can determine the absolute entropy of a substance if we make careful calorimetric measurements. So we take experimentally, we can determine the temperature dependence of a substance's entropy. So we can experimentally determine how entropy is related to temperature, and using this relationship we can derive the absolute entropy values for a substance. So we can tell the absolute entropy value for water or carbon dioxide at a specific temperature. Generally, these experiments are performed under standard thermodynamic conditions, which you can see here. So this gives us the standard entropy value for a substance. So experimentally, we can determine the entropy value at any temperature, generally at 25, for any substance. You can see some of these values here. You have a much larger table in the appendix in your textbook, but again, you can see here that using this relationship between temperature and entropy, it allows us to determine the absolute entropy, or how much entropy a substance has at a given temperature. Now, if we see standard entropy, we know we're talking about that at standard conditions, so 298 Kelvin. So the standard entropy change, now that we know how to figure out the entropies of substances, the absolute entropies, it allows us to calculate the entropy change for a system, where the system is a chemical reaction or a physical process. So the standard entropy change for any process can be computed from the standard entropies of the reactants and products. So we can use the following formula. The entropy change for a system is equal to the standard entropies of the products minus the standard entropies of the reactants. So if we have a reaction like this, A moles of A plus B moles of B yields C moles of C plus D moles of D, the equation we could expand to what you see here, where the change in entropy of the system under standard conditions is the entropies of the products, the sum of the entropies of the products, times however many moles we have, minus the entropies of the reactants, the sum of those, times the number of moles of each of the reactants. So let's use that formula and see if we can calculate the entropy change for this reaction using the standard entropies. So write this down, then I'll put up a table that you can use for the values. So pause the video in just a second and see if you can calculate the entropy change for this reaction. Here's the values we'll need. Okay, so here we want to use the formula. The change in entropy under standard conditions is equal to the entropy, the absolute entropies of the products minus the entropies of the reactants. And if I look at this, I've got N2O4 gas going to 2 NO2 gas molecules. So I'm increasing the number of gas particles. So right now I can look at this and I know the entropy change should be positive. And you can review that back on how to predict the signs of entropy changes. But we want to calculate the actual value. So I take the entropy of my products times 2 minus the entropy of my reactant times 1. I plug in the values that I get from that table or from the appendix in your textbook, and I calculate this, and I get the entropy change for this reaction is a positive 175.8, and remember your units, joules per Kelvin. So let's try one more problem. Calculate the change in entropy for this system, for this reaction, using the standard entropies. So I'll put that table up again, pause the video, and try to calculate it. Okay, so to calculate the entropy change for this system, we want to use the same formula. We want to find the entropies of our products minus the entropies of our reactants. And again, we have to take into account the stoichiometry, the number of moles. So I'm going to take the entropy of my product, ammonia, times 2 moles, minus the entropy, the sum of the entropies of nitrogen times 1 mole, plus the entropy of hydrogen times 3 moles. So our equation should look like this. Remember to include your units. Don't take any shortcuts. And if we solve this, we should have a negative 198.7 joules per Kelvin as the entropy change for this system. And if you look, we're going from 4 moles of gas to 2, so we would predict the sign of the entropy change here to be negative. So we should be able to see that that seems like a correct calculation. So be sure you understand the third law of thermodynamics, and you can use the formula in order to calculate the change in entropy for any system.